Love that. All right, at the very top of the notes, let's go ahead and write that limit notation because that is easy to forget. And I haven't looked at it for a year, so I might have forgotten it as well. Okay, so we're going to say that the area under the curve is the limit as n approaches infinity. And what's the n stand for? The number of rectangles, or they'll call them subintervals. So the number of subintervals. In this case, so if you're talking about a limit and n goes to infinity, you're saying you're doing infinitely many rectangles so that you can get an accurate portrayal. Okay, and then what do we have?
1 over n
Not looking at the last example, but looking at the formula. Yeah, so change in x. So change in x times f of x1 plus f of x2 Okay, and is it possible for me to shortcut this? Or do I always just have to write out everything that I'm adding repeatedly?
Can we shortcut it?
You put f and then the parentheses.
There's a little bit more you have to do.
Like n over e sign?
Yeah, well, it's the sum sign. So we're adding up a lot of different things. And so if you want to shortcut this notation, you could take this part out and you could just say summation from I equals 1 to n f of xi. So when you say I equals 1 to n, it means plug in 1 for I, and then add, plug in 2, plug in 3, plug in 4, plug in 5, all the way up to n, and add all those together. Okay, and then let's also write what delta x actually is represented by, or what delta x actually represents. What does delta x represent? For this formula, what does delta x mean? B minus a divided by n. So it's the upper bound of the domain that you're given minus the lower bound of the domain that you're given divided by how many subintervals you are or how many rectangles you're making. And that's just to make sure that your rectangles are equal widths. Okay. All right. So let's go ahead and look at this. So we're going to sketch the approximations. We're not going to figure out what they are. We're just going to sketch them. So this one says that we are doing the interval from 1 to 3, and we are going to have 6 subintervals. So what should I figure out so that I know how to draw my rectangles? Yeah. So we're going to say delta x is going to be 3 minus 1 over 6. 2 over 6, which is 1/3. And so that means that each of the rectangles has to be 1/3 of a unit wide. So 1/3, 1/3, 1/3, 1/3. Okay, and when it says left endpoints, what does that mean? Yeah, so we're going to draw this line up and we're going to connect it on the left side. So there's our first rectangle. Is this going to be an overestimate or an underestimate?
Over.
It's going to be an overestimate. And then here's our second rectangle. Third. Yeah.
And basically, I'll just throw them around.
That's gonna make things a lot easier. Alright, who wants a ruler? Keep going.
Actually, no, don't give me one of those crackers. Wait, are they the bendy ones or no?
I can give you a non.
Just little rulers. Yeah, give me a non-bendy one, please.
All right, the next one says that we are going to draw right endpoints. We have the interval from 1 to 4, and our subinterval is 4. We need to divide it into 4 subintervals. So we're going to say delta x is 4 minus 1 divided by 4. Did you grab everyone one but yourself? Oh, you have one. Yeah. 4 minus 1 divided by 4 is 3/4. So these intervals are 3/4. So I'm dividing each of my 1 units into 4 so that I can count out 3 of them. So this time I'm going up on the right to start each rectangle. Is this one as obvious about being an overestimate versus an underestimate? Yeah, it's kind of, there's a little bit of give and take there, right? So overestimate for that one, but underestimate for this one. Overestimate for this one, but underestimate for that one.
It looks like a little bit more than underestimate. Just a tiny bit more flat space than underestimate.
Yeah, I could go for that.
Yes.
Yeah. Okay. And then for the last one, it says midpoint. So we're going to say delta x is 4 minus 2 divided by 3.
Mm-hmm.
2/3.
Oh, divided by 3.
Mm-hmm. So 2/3. So starting at 2. All right, so 2/3, and this time we're doing a midpoint. So even though this is going to be the ends of my rectangle, I'm actually going to go up using the midpoint because that's what's going to determine the height of my rectangle, is the middle of the rectangle instead of the left side or the right side. I can't remember if I used this word or not. I guess I could look at my notes from last night. But when you use rectangles to find areas like this, these are called Riemann sums.
Yeah.
Yes. Okay. Yeah, we're going to write it again. Because sometimes they'll say, like, find the area of the rectangle, but sometimes they won't. Sometimes they'll just say find the Riemann sum. And so you have to know what that word means.
Wait, so how do you do the ones for 3? Like the division of it? Not squares.
I just divided it into 3. Each of the units I divided into 3, and then I just counted 2 of them. Okay. Are we good with those drawings? We got those? Okay. Next says, let A be the area under cos x on 0 to pi halves. So let's go ahead and think about this is, don't draw darkly, but this is the part that we're trying to find the area of. Find the area using midpoints and 4 subintervals, and then write an expression for A as a limit. Okay, so we're going to be doing the midpoint formula, 4 subintervals. So we're going to say change in x is pi halves minus 0 divided by 4. So that's pi halves divided by 4. And so like Toby said, that's pi eighths. Huh? Yeah, like in the drawing. That helps you. Okay, so I'm going to go ahead and write those out. So that means that if I'm going to go ahead and write this in terms of, did you guys see that? Like my whole lead fell out. The whole like, cool. So change in x if we were to keep it in terms of n, because we're going to write this using the limit notation in a little bit. I'm going to go ahead and say that this is pi halves minus 0 divided by n, which would be pi halves over n, which would be pi over 2n. So I'm just going to keep that in mind because we are going to use that in a little bit. Okay. So in the notes from last night, go ahead and look at your notes from last night. There was a point where I wrote xi equals, and I want to use that to find the other numbers on here so you guys can see how to use that part of the formula. So what did I say for xi equals?
Change in x times I plus a.
So times I plus a. Okay, so a is where you started the interval. So in this case, the a would be 0, right? The I is going to be going up by 1s. So interval 1, interval 2, interval 3, interval 4. And then the change in x is pi eighths. So if we think about this, our first interval is going to be pi eighths times 1 plus 0, which means our first interval is at pi eighths. Our second interval is going to be pi eighths times 2 plus 0. Pi eighths times 2 is 2 pi eighths, which would be pi 4. Pi eighths times 3 plus 0, 3 pi eighths. And then pi eighths times 4 plus 0. Pi halves, which is the right end. Okay. Now it says that they want us to use midpoints. So I'm going to go ahead and draw this up in the middle just so I can see what the height of that rectangle should be. Okay. And then for the next one, I'm going to go ahead and draw that up in the middle. And then for the next one, I'll go ahead and draw it up in the middle again. Okay. So for the midpoint Riemann sum, using 4 rectangles, the width of my rectangle is what? Pi eighths. And the height of my rectangle is going to be the function evaluated at the midpoint. And what's the middle of 0 and pi eighths?
1.
Pi sixteenths. Does that make sense? The middle of 0 and pi eighths would be pi sixteenths, right?
Yeah.
So we're going to say the width is pi eighths times cos of pi sixteenths. Okay? Plus, so that takes care of our first rectangle. The next rectangle still has a width of pi eighths, But if this is 1/16, 2/16, what's the height of the next one? 3/16 cos 3 pi 16. There's our next one. All right, then the third rectangle is pi 8, and then cos 1/16, 2/16, 3/16, 4/16, 5/16. There's our third rectangle. And then last we have pi 8 times cos 7 pi 16. Okay, so if we want to shorthand this, we can pull out that GCF of pi 8. So that width is the same for all of them. And then we can just say the height of the first one plus the height of the second one plus the height of the third one plus the height of the fourth one. No, cosine with numbers plugged in being added together doesn't have that property, and so we can't do that.
Yeah, there's no way to like do like a
no, and you're gonna find that these are annoying like that. So how did I show you guys how to do this on your calculator?
just plug it in there.
Make sure you have all your parentheses in there. This is cos, and it's a pi, so what should our calculator be in? Radians. Okay. So pi 8. I will say I was tutoring a student. We changed something into degrees, and then after that I was so frustrated making an answer key because I knew my answer was wrong and I couldn't figure out why. I was in degrees. All right, so we've got cos of pi 16 plus cos 3 pi 16. I'm about to take my calculator away, so you're gonna have to do it too. 5 pi 16. I don't hear very much clicking. And my calculator's gone. I wonder what the answer is. I know, but you don't. Don't shout it out. What I ran into last year is a lot of my calculus students were like, Miss Rice, I don't need a calculator because you're my calculator. And then they couldn't get the calculator active questions right. So I'm making you do it. Type it, type it, type it. Do again, where are you typing it? Go get a calculator. There's some in the back.
Okay, no, just do one hand. I just make this one.
Sure, go for it.
I usually guess like, I don't know, point. I guess what is the thing? 2, 3, 4. No.
Everything ever was pi. We discovered
Probably pi.
All right. How's our typing going? Typing? Typing good?
You don't need pumpkin pie, Alex.
I do.
Okay.
How we doing with the typing? We close?
Do we have to put
We'll start reading
like
pi by
pi over 8 parentheses, cos? Is there another parentheses?
It would look like this typed in your calculator.
Because I did it wrong at first. I didn't put the divided by 16, I just put pi 16. Because I heard you say like pi 16, so I just put
Pi times 16 instead of divided by. Yeah.
That's what I call tragic.
Yeah. So, but that's exactly the reason why we're typing it, right? It's because you look at it up here and you're like, I can type that.
Maybe I can be an example for years to come now.
Yes, appreciate it. 1.006. We would say unit squared technically, but I'd say most of the time they don't ask you for units on ones unless they explicitly give you units. So, okay, so if we were to write this in the limit notation, we would say the limit as n goes to infinity. And then the first thing we have to do is put the delta x in there, but it's the general case. So it's not saying that there are 4 subintervals, it's saying for any number of subintervals you could possibly have. Okay, so what should we put? we should put pi over 2n because this is for 4 subintervals specifically. This is for any possible number of subintervals I could ever want to have. Okay, so I'm going to say pi over 2n. And then we're going to do the shorthand way. So we're going to say summation from I equals 1 to n. And then we have to do the function evaluated at xi. It starts off with 1 and then it goes to 2, 3, 4, 5, 6, 7. It always starts at 1. Yeah. Now, when we did our xi, we did it specific for the problem that we were doing with 4 subintervals. So if we're changing this now to make it for infinitely many subintervals or any number of subintervals you want, what should I have instead of pi 8s? I should have pi over 2n. Okay, so it says, the formula says the function f evaluated at xi. Our function isn't f this time. We actually know what it is. What's our function? Cos. Okay, so I'm going to say the sum of cos, and for for xi, I'm going to say 2, just kidding, not 2, pi over 2n times I plus 0. I'm putting it there because these are my notes, and I just want to make sure that I know that it's the lower bound.
But if you don't put the 0.
If you don't put the 0, you're not wrong. Nope, I'm just putting it on my notes so that I don't forget that there's something there. Yep. Okay. How do you guys feel about that? We okay? Yeah, we got lucky on that one. All right, next example.
So we're okay. That was a very strange noise.
All right, given. Do you guys love this function or do you love this function? Are you ready to type stuff into that? Oh man, okay. So first it says find the area under the curve using 6 subintervals. They want to use right endpoints and then 6 subintervals with left endpoints. Whew, okay.
So 12 intervals overall.
Well, just 6 intervals, but doing it twice. Yeah, do the problem twice. So we're going to say delta x equals 2 minus negative 1 divided by 6. And so how wide are the subintervals? 1/2. Okay. If you guys would like to draw these, you can. I'm going to use colors, and I'm going to do a light color, and then I'm going to draw on top of it with a darker color. So if you want to go grab colored pencils, markers, whatever, so you can draw this, that's not a bad idea.
Marker isn't matter.
Well, if you start off with a color like yellow.
Or pink. Yeah, but it's going to bleed into itself.
Not if you do it right. Wait, that's mean. I can't tell color. I do.
I just need $1,000 over.
You're in Blizzard products and I'm disgusted with you.
It's a food that I got as a Christmas gift a while ago.
All right.
Okay.
So we're using right endpoints. Okay. So I went ahead and I cut them all in half. And I'm starting on what would be the right end of the rectangle. That's not very straight. Good thing my marker is erasable.
Okay, so please make young Johnson upset.
I totally missed it. Okay, so there's my first rectangle. There's my second rectangle. Okay, and I'm going to go ahead and write this as I do it. So what? You always do the curve to the x-axis. So if it's above the x-axis, you're going to be kind of like under the curve the way we think of it. If the curve is beneath the x-axis, you're going to do towards the x-axis, so it's going to feel like it's above the curve. But it really means just draw it between the curve and the x-axis. Because if you drew it on, if you drew it on the other side, you'd be drawing it forever. That would be terrible. Yeah. No, we're not going to do that. All right. So the width of my rectangle is 1/2. And how do I figure out the height of my rectangle for the first one? The function, and what x value would I plug into the function? -1/2. I'm going to say f of -0.5. I'm going to write it as I draw. So I'm going to write f of -0.5 because that's a little bit easier than me actually writing that function out, plugging 0.5 in. You guys okay with that? Because I'd have to write it for all of that, and that'd be like a lot. Okay, so there's my first rectangle. My second is 1/2 times f of 0, right? Okay. My third rectangle would be a width of 1/2 times a height of f of 0.5. Then my fourth would have a width of 1/2 and a height of f of 1. And then 1/2 and a height of f of 1.5. And then last would be a width of 1/2 and a height of f of 2. Whew. Isn't that fun? All right, so yeah, I don't know about you guys, but let's shorthand this a little bit. So I'm going to pull the 1/2 out of all of that. And I'm going to say f of -0.5 plus f of 0 plus f of 0.5 plus f of 1 plus f of 1.5 plus f of 2. That's going to be my shorthand way. Huh? Yep. Yep. If you were prepared for that, that's great. Okay. Now, when you do these problems, you are not allowed to round until the very end. Whenever we work in calculus, we don't round to the very end. So if we get a decimal answer, in the beginning of a problem, we have to store it in our calculator and save it for later. Okay? So if you were to find f of -0.5, you'd have to plug it in here and then store that decimal. And then plug in 0 and get that answer, and plug in 0.5 and store that decimal. And then plug in 1, and then plug in 1.5 and store that decimal, and then plug in 2, and then you'd have to add all those up, and that sounds like a pain, doesn't it? Yes. What do you mean negative? You can't. It's the same reason you can't do it to cos. Because the properties doesn't work like that.
I'm saying
so
we do -0.5 cubed minus 3.5 squared plus 2 -0.5 minus 1 in parentheses plus.
Yeah, that also sounds miserable. That sounds miserable. So here's what we're going to do that's even less miserable than that. Go ahead and hit y equals. Go ahead and hit y equals. And we're going to type it x to the third minus 3x squared plus 2x minus 1. And then we're going to get out of that. Go second, quit. Okay. This process is a pain in the butt, but it's not as much a pain in the butt as if you did what I just told you. Okay? So hit the vars button. Second mode. Hit the vars button.
It's right next to clear.
Go over to y-vars.
Function.
Number 1 function. We plugged it into y1. And since we know what f of 0 is, let's go ahead and do y1 of 0 just so we can verify that we're about to get it right. And we know if we plug 0 into this function, what should we get? Negative 1. So if you want to evaluate a function quickly, that's the way to do it. Okay? Now it's going to use a y1 instead of f, but we're about to use this process to get all of this. Okay? So we're going to type this in the calculator, but it's going to say y1 for each f that we have. Okay? Yes, it's a pain in the butt to get the y1 on the screen, but it's easier than what we would have had to do. You could go up and grab it. Yeah, that's fine. All right, so we're going to do 1/2 parenthesis, and then we got to get our y1 of all that stuff, and I should hear everyone typing, okay? So I'm going to do it, but so are you. Of negative 0.5. And be careful, because if you miss a parenthesis, then you're not going to have it. So it has to be y1 and then the parentheses around the number, not just times negative 0.5. It has to be of negative 0.5, of 0, of 0.5, of 1, of 1.5, of 2. So just double check, make sure you got your parentheses in there. All right, and then what do we have?
1.9375.
So the right endpoint Riemann sum is negative 3.9375. The area is negative because it's between the x-axis and the underside of the x-axis. So anytime you have an area that's under the curve like that, well, they're all technically under the curve. That's how they verbalize it. But when it's on the negative part of the y-axis, your area will be negative. When it's on the positive part of the y-axis, your area will be positive.
What if it's finding an area under the curve and our goal is slightly above it?
They'll kind of cancel each other out. Mm-hmm. So if you had a circle where half the circle was above and half the circle was below, it'd be an area of 0. It would completely cancel out. Right, but it's not talking about the area of the shape. It's talking about like a relation between an x and a y value of some sort of function, and in that case, you'd have things that were canceling each other out if you put a real life context to it.
I'm just going to have to wait for my brain.
Yeah. All right. So next, we're going to go ahead and do the exact same thing, but we're going to be doing the left endpoints. So if I go ahead and draw this one,
Oh, it goes all the way down.
yeah. You guys see how different that made my first rectangle? I am not going to color these in so that I can still see my other one.
You don't let it shoot the boat.
No, that sounds like a bad idea.
Okay. So when we type this in, 1/2, and so I'm going to go ahead and just start with that shorthand notation. So last time we plugged in f of negative 0.5 to find the height of the first rectangle. What should I be plugging in this time? F of negative 1. Okay, and then the next one is f of negative 0.5. And then f of 0. And then f of 0.5, and then f of 1, and then f of 1.5. And which one are we not using? f of 2. So if you didn't clear your screen, you actually don't have to type this again. You just have to fix one of them. So if we compare the right Riemann sum with the left Riemann sum, which one should we take away from the right and which one should we add in from the left? Take away f of 2 and put f of negative 1 instead. So what I'm going to do is I'm just going to go up here, and then I'm going to go to where the negative 2 is and type a negative 1. Yeah. So that was easy to fix. Go ahead and fix it on yours. And the answer is a lot different. Why do you think the answer is a lot different?
It's a lot different.
Yeah, the yellow, when I did the yellow, we had lots of underestimates, right? And then when I did the green, we have lots of overestimates. And so those, between the other one being a big underestimate and the new one being a big overestimate, our numbers should be a lot different, right? All right, so what did you guys get for the left Riemann sum?
-6,
Perfect. Yeah,
or decreased by 3.
but a bigger negative area. Yeah. All right, so let's go ahead and we're going to set up all the different pieces so we can write this as a limit. So delta x is how we start off, right? We need that in the limit notation. So I'm going to say 2 minus negative 1, but I'm dividing it by n because I'm looking for the formula. I'm not saying a specific number of subintervals. I'm just going to look for the formula. So 2 minus negative 1 over n would be what? 3 over n, okay. And then our xi would be what? Think about the formula. Plus negative 1, I'm just going to put minus 1. Okay, so this is one part we need to write the limit notation. This is the other part we need to write the limit notation. Okay, so I'm going to say the limit as n goes to infinity and what should I put next? Before that. Before that. No. Look back at your formula. 3 over n. So your delta x is the next thing that happens, and then you have summation. I equals 1 to n. And now with a function like this, they would probably just do f of and put the inside. Okay, but I'm going to go ahead and write it all out because I want you guys to see it. So I'm going to say x to the third minus 3x to the second plus 2x minus 1. And what do I plug in for x in all of those? The xi. 3 over ni minus 1, 3 over ni minus 1, 3 over ni minus 1. I put it in for all of them. So that was me plugging that into the function, and since this is all like one function, I'm going to go ahead and just show that using brackets. No. Look how ridiculously drawn out that was.
Why are we believing in each other?
All right.
Is
Now,
there any nicer way to write that?
just doing f of instead of plugging each of these different terms and just saying f of 3 over n. Yeah. So the thing about this is whenever you when you are approximating the area under a curve and you're using rectangles, there's not really a nice way to shorthand it. Even the shorthand ways are obnoxious. And so this is our introduction to integrals, so eventually we're going to stop writing all this longhand notation. But for right now, it's going to be obnoxious. That's just kind of how it works. Yep. All right, so let's look at the next one. With this one, it says the rate at which water is being pumped into a tank is given by a continuous and increasing function R of t. A table for selected values of R of t for the time interval 0 to 13 minutes is given below. They want us to use right Riemann sums and 4 subintervals to approximate the area under the curve. Now, we have only looked at Riemann sums where they had equal subintervals, but if you look at this, are the subintervals going to be equal? They are not. Okay, the first subinterval is going to go from 0 to 4. The second subinterval is going to go from 4 to 6. The third one's going to go from 6 to 10, and then the fourth one's going to go from 10 to 13, and there's no way to avoid it. Okay? No. 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 Nope. So, the right Riemann sum, nope, it's not allowed. It's not allowed. It is wrong. It is mathematically wrong because if you were to do it, you would be assuming that they're linear in between the points, and they're not. Yeah. All right, so the right Riemann sum, what is the width of the first subinterval? 4. Okay? And if we're using a right Riemann sum, should I use a height of 7 or a height of 13? 13, because that's the right side. Okay, so there's my first rectangle. What is the width of my second rectangle?
4 to 6.
4 to 6 is 2, a width of 2. What's the height? 18. What's the width of my third one? 4. What's the height? 23. What's the height of, or what's the width of the last one? 3. What's the height? 27. Okay. So with this one, we don't have that GCF of a width to pull out. We really just have to type it in like that. Now, this is probably going to be calculator. Yeah, this is probably going to be a calculator inactive question. So put your calculator away. We're going to multiply these by hand. 4 times 13, 4 times 10, plus 4 times 3, 52. Did you say 50 or 50? 52. 36. 4 times 20, 4 times 3.
4 times 3 is 12.
So 92, 80 plus 12. All right. 3 times 20. 3 times 7. So 20 plus 20, no, 60 plus 21, 81? Okay. We got to add all those up. No. Yeah. 11, got it. 10, 15, 11, 26, 261. I was shaking my head at you because you were losing my train of thought. You were ruining it for me. Don't shout out the answers while I'm doing mental math. That hurts my brain. All right, we have to figure out what our units are. So here's the easiest way to figure out your units. We're going to look at the units of what we multiplied. So the 4 had what kind of units? Minutes. So we said 4 minutes times the 13 had what units? Gallons per minute. And so when we look at that, the minutes cancel, and the answer is just gallons.
It's not minutes per gallons.
Nope. Because you're not doing a rate of change. You're not doing derivatives. What does this represent? Okay, so think about this. What does this represent? So we're going to say for time 0 to 13 minutes, 261 gallons of water was pumped into the tank. All right. Wasn't that fun? I had fun. Woo. All right.